Good morning, everyone. I am Ritika from BSc Chemistry Honors Final Year. Today's my topic for presentation is NMR spectroscopy. Principle of NMR spectroscopy. It involves transition of spin-active nuclei from ground state to excited state by the absorption of RF radiations. Then there is a correspondence in between the frequency of incoming RF signal and that of the medium in presence of applied magnetic field. The energy associated with NMR technique is radio frequency radiations are incapable of breaking the weak covalent bond. So NMR is a non-destructive technique. The NMR spectroscopy involves only one type of nucleus at one time. Relaxation process: the process in which the excited nuclei get deactivation from higher energy nuclear spin state and returns to the ground state by loss of energy without emission of radiations is called relaxation process. Types of relaxation process. There are two major relaxation process. First, spin lattice longitudinal relaxation, and second is spin transverse relaxation. First, spin lattice relaxation. The loss of excess energy by interaction in between excited nuclei and surrounding environment is called spin lattice relaxation. Second, spin relaxation. The loss of excess energy by interaction in between excited nuclei and neighboring spin active nuclei with identical precessional frequencies but differing magnetic quantum states is called spin relaxation. Relaxation time. The average lifetime of nuclei in the higher energy state is called relaxation time, or the time taken by a certain group of nuclei to lose of their fraction of excess energy during relaxation process is called relaxation time. Effect of relaxation time on the width of the signal. The effect of relaxation time on the width of the signal is given by Heisenberg uncertainty principle. Del E into del T is equal to H into del V half into TV is less than H, or del V half is inversely proportional to T1. If the relaxation rate is too fast, then line width increases. In the resultant NMR spectrum is observed. The broadening of signal occurs if paramagnetic impurities such as oxygen, magnetic materials, ions, etc. are present. If sample is solid or viscous because spin relaxation process becomes fast in solid and viscous liquids than in gases and dilute solution. So to get sharp signal, always avoid paramagnetic impurities in sample. Always avoid use of solid and viscous liquid as sample and use dilute solution because in dilute solution the molecules are more free to move. So the relaxation process are not very fast. NMR spectrometer. Essential features of NMR spectrometer are: first, sample probe. The device which holds the sample is called sample probe. It is placed in between the two magnets. Second, powerful magnet. Strong magnetic field are necessary for NMR spectroscopy to produce homogeneous magnetic field and to get a signal with high resolution. Unit for magnetic flux is the Tesla. Modern NMR spectrometers use powerful magnets having field of 1 to 20 Tesla. The magnetic field strength can be changed continuously over a small range using sweep generator. Relation between frequency and magnetic field. V is equal to lambda by 2 pi into h naught, where gamma for 1h1 is 267.53 radian or Tesla. NMR spectrometer. Radio frequency oscillator. Even with this high field, the energy difference between the two spin states is less than zero point 0.1 calorie per mole. Further, infrared transitions involve 1 to 10 kil per mole, and electronic transitions are nearly 100 times greater. So, radio frequency oscillator is installed perpendicular to both applied magnetic field and sample tube, which transmit radio frequency radiations as a frequency in unit of megahertz, ranging from 20 to 900 megahertz, depending on the strength of magnetic field and the nature environment of nucleus being studied. Fourth, radio frequency receiver or detector. It is very sensitive as the signal levels are very small, so multiple amplification of signals is required before they are sent to output devices. Fifth, recorder or integrator. The recorder records the spectrum as a plot of the resonance signal versus the strength of applied magnetic field. The strength of the signal is directly proportional to the number of nuclei resonating at given applied magnetic field. The automatic integrator can automatically measure the area under the observed signal, and that area is directly proportional to the number of resonating nuclei giving the signal. Ways of operating NMR spectrometer. There are two ways to operating NMR spectrometer. The first is constant radio frequency NMR spectrometer. Fix the frequency of incoming radio frequency radiations and change the strength of applied magnetic field to make correspondence between the frequency of incoming radio frequency signal and that of the medium for resonance to get NMR signal. Second, constant magnetic field NMR spectrometer. Fix the strength of applied magnetic field and change the frequency of incoming radio frequency radiations to make correspondence between the frequency of incoming radio frequency signal and that of the medium for resonance to get NMR signal.